Hey everyone and welcome back to SP Learning Labs. In this module, we are entering a very practical part of Python programming, concurrency. Concurrency simply means doing multiple tasks at the same time or at least feeling like they happen together. Don't worry, I'll explain everything gently with simple real-life examples. Introduction. Before we start, let's think about something from real life. Imagine you have 5 chores to finish at home. You need to wash clothes, boil water, charge your phone, download a movie, and reply to WhatsApp messages. If you do everything one by one, it takes a long time. But in reality, you don't. You put clothes in the washing machine while the water is boiling, while your phone is charging, and while you text for friend. This is concurrency. Many tasks happening together or switching so quickly that it feels like together. In this lesson, everything will be explained in a friendly way so you fully understand what concurrency means, how threads helps, how async helps, what CPU bound and input-output bound tasks are, how to pick the right to OI, how to debug concurrency, logging, monitoring, safety and code reliability. By the end, concurrency will feel simple and natural. In the previous module, we learned testing in Python, how to verify that programs works correctly, how to use asserts, test cases and testing tools. Now, we learn how programs handle multiple tasks together because testing and concurrency work hand in hand when building real applications. Imagine one cook working alone in a kitchen. He cuts vegetables, then waits for rice to boil, then washes dishes, then fries paneer. He does everything one by one, slow, tiring and time consuming. Now, imagine 3 cooks in the same kitchen. One cuts vegetables, one boils rice, and one fries paneer. Suddenly, everything feels fast. That is concurrency in Python. Introduction. Why concurrency matters? Concurrency is a powerful, but if misused, it can break your program in confusing ways. A few beginner mistakes include adding threads everywhere thinking it increases speed, ignoring the GIL, not adding error handlings, mixing CPU and input-output tasks incorrectly. The goal of this module is simple. Learn to choose concurrency wisely, write safe code and understand when to use which tool. If you understand this module clearly, you will be able to write a real-world concurrent programs without fear. Concurrency foundations. What is concurrency? Concurrency means your program handles multiple tasks at once, but not always exactly at the same second. Parallelism means truly simultaneously, like multiple cooks actually cooking at the same time. Sequential execution is simple, one task after the another. Concurrency is like switching between tasks quickly and smartly. Parallelism is like actually running tasks together using multiple workers. Here are simple ways you understand. Sequential, one cook handling one dish at a time. Concurrency, one cook preparing ingredients for multiple dishes, switching between tasks. Parallelism, multiple cooks each handling a separate dish at the same time. Think of concurrency as multitasking. Think of parallelism as teamwork. Input-output bound versus CPU bound tasks. This is one of the most important parts of concurrency. Input-output bound tasks. These involve waiting for external resources, waiting for API data, waiting for database queries, waiting for file read or write, waiting for network downloads. The actual CPU does very little, mostly waiting. CPU bound tasks. These involve heavy computations, image processing, mathematical calculations, compressing data, ML model operations. Here, CPU works non-stop. Mixed workloads. A web scraper is a great example. It waits for websites to respond, then process the HTML. Knowing whether your task is input-output bound or CPU bound allows you to pick the correct concurrency tool. Common errors. A common mistake, mixing up concurrency with parallelism. Another mistake is expecting speed improvements for CPU tasks using threads, which is not true because of the GIL. Always first understand whether your task is waiting or computing. Never mention facts. Here are the things most tutorials skip. Switching between threads has small overhead. Switching too often can slow things down. Cooperative multitasking, like Async, needs the program to yield or allow others to run. If one task never yields, others get stuck. Async works amazingly well when your tasks mostly wait for something. These small details make a huge difference in the real systems. Choosing the right concurrency model. This is the heart of this module. Input-output bound tasks using threading or async. Example, multiple web requests, reading files, downloading images. CPU bound tasks. When your program spends most of the time doing calculations, threading will not help because of the GIL. Instead, you use multiprocessing because each process uses a separate Python interpreter. Examples, matrix multiplication, simulating physics, generating large number sequences. Hybrid workloads. Some tasks require both input, output and CPU. A good example is a web scraping. Fetch 100 pages from a website, input-output bound. Use threading or async. Process extracted text. CPU use multiprocessing. This mix and match makes programs fast and also efficient. Profiling and debugging concurrent code. Before optimizing anything, always measure first. Use time measurements to find slow paths. Find whether the delay is coming from the network, CPU, disk, or from your own code. For example, you may use a simple timing method to see where bottleneck occurs. Profiling tools help you to understand exactly where time is being spent. Tools for profiling. Some commonly used tools. cProfile shows which function to make the most time. Async, profiler or similar tools help measure async and threaded performance. Snakewiz visualizes profiling results. You don't need to master these tools immediately. Just know they exist is enough for you. Logging and monitoring. Logging is very important in concurrent programs. Instead of guessing what thread or process is doing, logging tells you exactly which thread is running, which process is active, what file is being handled, which step failed. This is like security cameras in a building. They let you see what's happening behind the scenes. Practical guidelines for writing a safe concurrent code. Here are some simple but powerful rules. Don't use concurrency if you don't need it. Sometimes sequential code is faster and easier. don't add threads or processes too early. Measure first, optimize later. Add concurrency only where it clearly helps. As a simple example, if you need to process 10 tiny files, multiprocessing may be slower than simply reading them one by one. Start simple, then optimize. Always write a simple version of your program first. Run it, measure it, understand where time is being spent. Only add concurrency when you are sure it helps. This avoids over-engineering and keeps your code simple. Handle exceptions properly. Concurrent programs. Concurrent programs must not crash the entire application because of one small failure. Wrap tasks in try except blocks. Make sure one failure doesn't stop the whole pipeline. In process, ensure that every worker handles its own errors safely. Clean and shut down. Resource management. This refers to closing threads, process and resources properly. Things to remember while doing this. Close threads when done. Close pools. Handle queues properly. Avoid creating zombie processes. Use context managers where possible. Proper shutdown. Proper shutdown prevents memory leaks and hanging programs. Avoid over-engineering. More threads and more process does not equal more speed. Sometimes increasing concurrency can slow down the program, increase overhead, create debugging problems. Using concurrency only where it truly helps. Here are few tricky questions for you. What is concurrency? Handling multiple tasks at the same time or switching between them efficiently. What is parallelism? Truly running tasks at the exact same moment using multiple cores. What are input-output bound tasks? Tasks that spend time waiting for external resources. What are CPU bound tasks? Tasks that spend time doing heavy calculations. When use async for many input-output tasks that involve waiting. When use multiprocessing for heavy CPU calculations. What is over-engineering in concurrency? Adding concurrency where it isn't needed, making code slower or complicated. And that brings us to the end of concurrency, threading and async basics. Now you understand what concurrency really means, how to handle input-output and CPU tasks, how to avoid common mistakes, how to choose the right concurrency model, and how to write safe, clear concurrent code. In the next module, we'll go deeper into one of the most powerful tools in modern Python, threading in Python. We will learn threading step by step with simple, real-time examples. So now you understand how to use threads safely and correctly. See you in the next video. That's it for today's session. Like, share and subscribe to SP Learning Labs.